Okay, I've improved my model now. I've got the fringes at the coordinates 0, 0, so that it doesn't wildly head off in one direction. So this is what you see. So that's what you see on the screen. You see this interference. Like that. This interference pattern. That's all you see. You don't see anything else. So how is it understood? Normally it's considered to be a probability wave. And so it's said that the particle, photon or whatever, just heads along a constructive interference line. So at the moment it's heading along 1, m equals 1, m equals 2, m equals 3, m equals 4, and then it's out of bounds. So this is the probability wave. Normally they use the phase waves and interfere phase waves because you actually end up with the same angle. But the probability wave is not the same as the phase waves, because the phase waves are electromagnetic radiation, and the probability wave is something different. So what's the real correct interpretation? Well, it is first of all, this is how they calculate it. You have your ideal double slit interference, and then you have your single slit envelope, and then you combine them by multiplying them together and squaring it, and you end up with your interference pattern here, which you see on the screen. That circle is actually the T, so it's actually giving the first minima because it's 1T. Okay, then I've got an example. There you go, there's an example from the book. You can see these red ones, I can line them up about there, about 0.3, no, yeah, somewhere around here, yeah, lines up. Okay, so what's the real answer? Is the t function. I think the t function is going to turn out to be the wave function, and so this is the actual screen. There's nothing outside this t function, and the fringes disappear outside the t function. So let's look at how come there's interference. I think it's because this is quantized, so y is quantized. So I'm stepping that, making it 1, 2, 3, 4. This is always a right angle here, and so it seems like that black line is actually the line of simultaneity that we from special relativity, and it seems to be quantized. So if you've got your slit 1 and you've got your slit 2 over this side, and if they're the same, then it's going to appear the fringe will be right in the middle. But if you've got an extra number on one side, say slit 2 is actually 1 while slit 1 is actually 0, then you've got an extra 1, or you might have an extra 2 constructive interference, or you might have an extra 3 waves coming out of that slit 2 interfering with that first slit, or an extra 4, and this causes the actual this is the screen, the actual particle to turn up there, and then you just whiz down and it'll show you the intensity. So for say y equals 2, you can see the intensity there. Y equals 1, you can see the intensity is 0.684, whereas for m equals 2, or y equals 2 in my case, the intensity is 0.171. And now notice, just going to get rid of that because it's don't really require it. Now notice that the y, if it heads outside the t function, there, it's gone outside, you can see 7, there it is. It's actually, then there's no fringe outside the t function, so then it's gone, there's no fringes at all. But if you come back, and now it's inside the t function, and it exists. So, but there are no fringes existing outside the t function. So where that black circle hits that red circle, goes outside, then there's nothing. But inside there is something. Outside there's nothing. Inside there is something. Normally I draw my relativistic slide rules, and this is probably the most common interpretation, which is time going forward, and then it just goes backwards. The purple one rejoins its entangled left side, which then collapses with the right side, and you end up with a collapsed particle on the screen. So that's collapse of the wave function. Time going forward, there it is, the purple one whizzing away, hitting the screen and collapsing. So you can choose other values. Now it's whizzing away, hitting the screen there at y equals 3, and then collapsing